An important result from linear algebra is that if you understand how a linear transformation acts on a set of basis vectors, then you understand how it acts on any vector. An arbitrary v isn't special, it's just a weighted sum of the e's. Because t is linear, knowing what it does to the basis vectors tells you everything about what it does to any input. In signals, we're going to build upon that idea to investigate DT-LTI systems. We treat input and output signals as vectors, and the most important basis vector is the impulse, also called the Kronecker delta. A DT-LTI system is a special kind of linear transformation. It's time invariant, but for now, let's just treat it as a black box. The impulse response, h of n, is defined as the output of the system when the input is a single impulse. An intuitive way to think about this is you kick the system once and you record how it responds over time. That response, how the system rings and settles, is the impulse response. Any discrete time signal can be written as a weighted sum of shifted impulses. Each impulse picks out exactly one sample of the signal. This equation for x of n is a compact way of writing what we drew above. Take an impulse at time k, scale it by x of k, and add all of them up, just as how it's done to make vectors from a basis. The impulses delta n minus k are playing the role of basis vectors for signals. Let's pause and make sure we really understand what linearity and time invariance buy us. We already defined the impulse response h of n as the output when the input is delta of n. And here's the key. If the system outputs h of n when I put in delta of n, what happens if I put it in a shifted impulse, delta n minus k? Because the system is time invariant, the output must just be shifted by the same amount. Nothing else can change. Now let's use the linearity of the system. Earlier we said any signal can be written as a weighted sum of shifted impulses. If we put this entire sum into the system, linearity tells us we can pass each term through separately and add the results. This equation is the key. Every linear transformation enjoys the ability to be completely characterized by what it does to basis vectors. DT-LTI systems have the added benefit that you only need one vector h of n to know how to find the output of arbitrary inputs. This operation, taking an input x of n and combining it with the impulse response h of n in this way, is called convolution. We write it compactly with a star symbol. When you see the symbol, you should remember that each sample x of k produces a shifted copy of the impulse response h of n minus k, scaled by how big x of k is. The sum of these is y of n, and that's what convolution does. You might also hear convolution described as flip and slide. That's more of like a computational trick. Once a system is DT-LTI, everything it does is convolution. There isn't any other behavior. So can the impulse response tell us anything about the system? If h of n is short, say it's only non-zero for 1 or 2 time steps, the system has very little memory. It only cares about recent inputs. On the other hand, if h of n lasts a long time, the system remembers inputs from far in the past. If the impulse response eventually dies out, the system is stable. A single kick doesn't cause the output to blow up forever. But if the impulse response grows, that means the system is unstable. Lastly, if h of n oscillates, there's resonance or ringing. All tuned percussion instruments, like glockenspiels, have oscillatory impulse responses. So just by looking at h of n, you can often predict what the system does before doing any math. Let's zoom out and summarize the big idea. A DT-LTI system is a linear, time-invariant operator on signals. Because of those two properties, everything the system does is determined by its impulse response. Once you know h of n, you can compute the output for any input using convolution. You can tell how much memory the system has, you can tell whether it's stable, and you can often predict its qualitative behavior without doing any math. That's why impulse responses are huge for signal processing. If you record how a room responds to a single sharp sound, a clap, you can predict how any sound will behave in that room by convolving it with that impulse response.